Okay, so we're continuing our work here, and we're going on to do some problems. Use the given derivative to find all the critical points of f. At each critical point, determine whether relative maximum, relative minimum, or neither occurs. Assume in each case that f is continuous everywhere. So we have the derivative already given to us, so we don't have to find the derivative. So to find all the critical points, we just need to find the zeros. So what we can do is we can write this in factored form. We can begin by factoring out an x, and that leaves behind 4x squared minus 9. There you can see that you have the difference of two squares, and so then we still have the x, don't lose the x. And then you have 2x minus 3 and 2x plus 3. From the factored form, you can see that the critical points, or that the zeros, happen at 0, 3/2, or negative 3/2. If you can't see those that easily, you can set each factor equal to 0 and get your critical points that way. We're not told how to classify them, so we either have the first derivative test or the second derivative test. And so because the derivative is very easy to find here, I'm going to go ahead and use the second derivative test. And so the second derivative of this function is 12x squared minus 9. You can see that when I put in the 0 into this problem, then I will get negative 9. Remember these three dots. These three dots mean therefore. So your second derivative is negative, so your graph is concave down. But you were looking at a point where your first derivative was 0, so you must be looking at this top point, and you have a relative max. So therefore, relative max. When we evaluate our second derivative at 3/2, we will get 12 times 9/4 minus 9. 12 times 9/4, 4 goes into 12. 3 times 9 is 27. And so you get 27 minus 9, which is 18. And so now that is positive. Again, that tells us that our graph is concave up. Since we were looking at the point where the derivative was 0, that tells us that we're looking at that point. And so again, therefore, we have a relative minimum. You can see that changing that 3/2 for negative 3/2 isn't going to change anything. So the second derivative evaluated at negative 3/2 will be the same thing, 18. And again, that will tell us that our graph was concave up. We were looking at the point where the first derivative was 0, so therefore we have a relative minimum. Okay, so for our next problem, same instructions. Use the given derivative to find all the critical points of f, and at each critical point determine whether a relative maximum, relative minimum, or neither occurs. Assume in each case that f is continuous everywhere. So we're given the first derivative already, but notice that in this case, to find the second derivative is going to be rather tedious. So rather than using the second derivative test, we'll use the first derivative test. Also notice that because in the denominator here we have this x squared plus 4, that is always a positive value. And so then that tells us that our derivative is never undefined. And so then the only critical numbers are the numbers that make the first derivative 0, and the only way you can make the first derivative 0 is if your numerator is made 0. So we can find the critical points simply by finding the zeros of the numerator, and so then the numerator is x squared minus 7, and we make that equal to 0. Can't factor here with integers, so we just go ahead and extract square roots, add 7 to both sides, so we get x squared equals 7, and so then x is equal to plus or minus the square root of 7. And so then those are our only critical points. So then to use the first derivative test, we draw the sign chart. And so then this is a sign chart for our first derivative. The numbers that go on here, the negative square root of 7 and the positive square root of 7, those are the only numbers that will make the derivative either 0 or undefined. And so those are the only numbers that need to go on there. You can, the square root of 7 is 2 squared is 4, 3 squared is 9. So the negative square root of 7 we can use something less than the square root of 7, so negative 3. And when you put in negative 3, you get positive 9 minus 7 is positive 2. And when you pick something in between negative the square root of 7 and positive square root of 7, you can pick 0. 0 squared minus 7 is negative 7. So everywhere in the middle it has to be negative. So we've gone over that before, that it has to be the same sign everywhere in between the zeros. And once you get past the square root of 7, then you can pick 3 again and you will get positive. If you pick 3, you will get 9 minus 7, which is positive 2 again. And so there we go. And so then that tells us then that we have a relative maximum at x equals negative the square root of 7, because we were going up and then started coming down. And then we have a relative minimum at at positive the square root of 7, because we were going down and then going up. And so there we go. More of the same. So use the given derivative to find all critical points of f, and at each point determine whether a relative maximum, relative minimum, or neither occurs. Assume in each case that the f is continuous everywhere. Okay, so again, critical points are where the derivative is 0. We already have the derivative given to us. It's already factored for us. And so then here it's not that easy to tell by inspection what the zeros are, so we can just set each factor equal to 0. So we can, x to the 4th has to equal 0, or e to the x minus 3 has to equal 0. For this one, the only number that you could raise to the 4th power and get 0 is 0. So that's one critical point. For this one, the variable is in the exponent, so we can work backwards. So we can first add 3 to both sides and get e to the x equals 3. And then natural log both sides, so the natural log of e to the x will equal the natural log of 3. And then over here, the natural log undoes the e to the, and you just get e, and so you just get the exponent, x equals the natural log of 3. So when you go to make your sign chart, the numbers that are on there now are 0 and the natural log of 3. You can punch the natural log of 3 into your calculator, but E is approximately 2.7. And so then when you natural log something, when you log something that's bigger than your base, just a little bit bigger than your base, it's going to be a little bit bigger than 1. When you choose a number that's to the left of 0, like say -1, when you put it into this factor, you will get a +1. And when you put it into this factor, e to the -1, again, is going to be less than 1. And so when you subtract 3, it'll be negative. So you will get a positive from this factor and a negative from this factor. And so then when you multiply those together, you will get a negative. Very common for students to think that, well, once I get one of them, I can just start switching them, right? For my sign chart. And that's not true. Once you choose something a little bit bigger than 0, like 1, yeah, 1 will do. Like 1, then you're going to get still going to get a positive from this one. And when you take E and raise it to the first power, that's 2.7 something, and you subtract 3, you're still going to get a negative from that one. And so then you're going to still get a negative. It doesn't switch. So at 0, you do not have a relative maximum or a relative minimum. And then once you get past the natural log of 3, if you put in 5, e to the 5th is definitely bigger than e to the 5th is definitely bigger than 3. So then when you put that in now, you will get a positive because this is going to switch. And so what this sign chart tells you is there is neither a relative max, no relative extremum, at x equals 0, and then you have a relative min at x equals the natural log of 3. If the back of the book calls for the y coordinate, then you substitute in these numbers into your original function to get your y coordinate. Right, next we want to use any method to find the relative extrema of the function. So again, here we are given the original function and we want to find the relative extrema. So the relative extrema we find by finding the derivative. So first we need the first derivative. Again, you need to look and see how your function is made. Your function is a product. It's x times this. We could expand this, but that would take too much time. So instead, we'll just use the product rule. The derivative of the first one is 1. Second one left alone. X minus 4 to the 3rd power. And then plus, we leave the first one alone, x, and take the derivative of the second one. But the second one is a composition, so we need the chain rule. So we bring down the exponent for the power function, take one away from the exponent, and so that the new exponent becomes a 2, but what's inside your base stays the same. Then we multiply by the derivative of the inside, but the derivative of the inside is 1. The derivative of x minus 4 is just 1, so we don't need to do that. To help us see where our critical points are, we can see that we have 3 factors of x minus 4 here, and we have 2 factors of x minus 4 here. So we can factor out 2 factors of the x minus 4. And when we do that, that will leave behind x minus 4 plus 3x. If I back distribute this, I will get the x minus 4 cubed, and then over here I'll get the 3x times the x minus 4 squared. We can clean that up a little bit, and this will be x minus 4 squared, and then x and 3x is 4x minus 4. So you can see that the only critical numbers are 4 and 1. And so then we can make the sign chart. So to make the sign chart, we make our number line. And the only numbers that go on here are 4 and 1. You can see that if you pick numbers to the left of 1, you will get a negative number inside, but when you square it, you will get a positive. And when you use numbers less than 1 here, like 0, you will get a negative. And a positive times a negative will give you a negative. Now, once you get past 1, like 2, 4 times 2 is 8. 8 minus 4 is 4. This expression will change. It's a line. It crosses the x-axis there, and it will change. And so now you will get a positive. But once you get past 4, inside the base changes from being a negative number to being a positive number. But the whole thing didn't change because you're going to square it. It's still going to be positive. It used to be positive. It still is positive. So again, these sign charts don't just change. And so again, we have a relative min at x equals 1 and no relative max. Okay, so then using the calculus, we can make an accurate graph for this with very few points. There's nothing happening outside of nothing interesting happening too far away from 1 or 4. So we could go to our calculator and put the formula into the calculator and get a table. And we could go from -1, 1, and we have this other critical point 4. Might as well plug that in. And then extend that out to 6. And then x, f of x. And at -1, calculator tells me it's 125. At 1, we get -27. We know that that is a relative min, -27. At 4, we don't need the calculator for that. When I put 4 in, 4 minus 4 is 0. Cubed is 0 times anything is still 0. And then at 6, the calculator tells me that we get 48. So what this tells me about my graph, we can put this together, that the graph is going to be decreasing until we get to an x value of -1. And at an x value of -1, we get -27. And to the left of that, it was decreasing. So we'll not worry about the concavity right now. We'll just draw it like that. And then at 4, we get to 0. But once we get past 1, we start increasing and continue to increase forever and ever. And we do have a flat spot there because my first derivative is 0. So we try and make a flat spot, something like that. And we'll worry about the concavity and the inflection points in a little bit. Then it just keeps growing and growing. But we need a little flat spot right there. Okay. Moving on to the next problem, same instructions. Use any method to find the relative extrema of the function f. So then find the first derivative. And then we get 2 plus 3 times 1/3 x to the -2/3. So this term is just a power function. We bring down the exponent, 1/3, take 1 away from the exponent. 1/3 minus 3/3 is negative 2/3. If we write this in this form, the 3 and the 1/3 make 1 over x to the 2/3. And then this can then be rewritten as 2 plus 1 over the the cube root of x squared. First, we could see that this function by inspection is undefined when x is 0. Next, we can see that because we're squaring this term will always be positive. And so then because we're adding 2, the whole thing will never be 0. A positive number plus 2 can't make 0. And so then the only critical number is at 0. If we find so the sign chart for this is not going to be very difficult, as I just outlined. So we'll use the first derivative test. So for the first derivative, the only critical number is 0 because there it's undefined. To the left of 0, we said this is always going to be positive. And so this graph just goes up and up and up. So a quick sketch of this is that the only critical number is at 0. When we put in 0, we get 0. The graph is always increasing, and it could look something like that. Always increasing. We could look at the second derivative test to get a better glance at what the graph might look like. But all we were looking for is the relative extrema, and this thing has none. So as we mentioned in section 4.1, we can use the calculus to help us graph more complicated functions. In pre-calculus, we didn't graph anything past the quadratic unless it was a special case, but now we want to give a graph of the polynomial and label the coordinates of the intercepts, stationary points, and inflection points. Check your work with the graphing utility. We're not going to worry about the intercepts, maybe the y-intercept because that's easy to find, but we're not going to worry about trying to find the x-intercepts. We're mainly going to concern ourselves with the calculus that we can get from this. Okay, so we'd like to know where this thing is increasing and decreasing and its relative extrema. So that is told to us by the first derivative. So first thing we do is we find the first derivative. Derivative of the 2 is 0. Derivative of the x is negative 1. Derivative of the 2x squared is 4x minus 3x squared. And again, to help us with the first derivative in our sign chart, it's favorable to have this in factored form. And so we factor out a minus 1. And then I like to have my terms in descending order. So I get 3x squared minus 4x plus 1. We can continue factoring. This isn't going to be very difficult to factor. It's a trinomial, so it's probably the product of binomials. The first terms here have to make 3x squared when you multiply them. And so there has to be a 3x and an x, not a whole lot of choices there. This is plus, but the middle is minus. So the only way you're going to multiply to make a positive and add together to make a negative is if they're both minus. And there's only one way to get 1. So that's 1 and 1. So either this works or this thing is prime and it has no integer or rational zeros. Okay, so these two would make minus x, these two would make minus 3x, and those two would make would make minus 4x. So we're good there. So next, first derivative test, we want to figure out what the critical numbers are. The critical numbers are 1 and 1/3. I don't need a scale, but they need to be in the correct order. So the 1/3 comes before the 1. Now, 3x minus 1 is a line, x minus 1 is a line. but we have this constant factor over here, -1. This is the sign chart for f prime. So to the left of -1, to the left of 1/3, everything is negative, but we also have this third negative over here, so we end up getting a negative output. In between 1/3 and 1, this one already crosses the x-axis, so this one will switch to a positive number, and then we will have two negatives and we will get a positive. Once we get past 1, then this one will cross again, and now we'll have two positives and a negative, and so we get a negative. This tells us that our graph to the left of 1/3 is increasing. Once we get past 1/3, it's decreasing, and then once we get past 1, it goes, I had that backwards. This tells us that our graph is decreasing to the left of 1/3. It's increasing once we get past 1/3, and then it starts decreasing again after we get past 1. The interesting behavior is all happening here in the neighborhood of 1/3 and 1. So that is what we need to look at. Okay, so we also would like to keep track of concavity. So we're going to look at the second derivative. So the second derivative is then going to be, we can get it from here, 4 minus 6x. And so then you could see that the only critical number, this is just a line, so the only number that's going to make your second derivative 0, that's not a critical number, I misspoke, is 6 divided by 4, or 4 divided by 6. 4 divided by 6, you can set it equal to 0, and that will give you 2/3. So 2/3 is your only is the only number that makes the second derivative 0. Since this is a line that goes down over here to the left of 2/3, it will be positive. To the right of 2/3, it will be negative. And this tells us then that our graph is concave up to the left of 2/3 and concave down. And so then you can see then that to make a complete graph of this, we only need 3 points. We need to know what's going on at 1/3. We know what's going on at 2/3. And we need to know what's going on at 1. Okay, so put this formula into your calculator and then use the table to make your table. And at 1/3, we get 1.85. And then at 2/3, we get 1.92. And then at 1, we get 2. It's cramped in there pretty tight. Okay, so we can then make a quick sketch. So to the left of 1/3, so at 1/3, we get 1.85. And then to the left of 1/3, by following your two sign charts here, you are decreasing and concave up. So that means you're bent something like that. And then once you get past 1/3, you start decreasing and start increasing, but you're still concave up until you get to 2/3. And you're not going up a whole lot. And then once you get past 2/3, then you are still concave. You switch to concave down, and you're still increasing until you get to 1. So when you get to 1, you are increasing and concave down. And then once you get past 1, you continue to decrease. Now, the scale there is not very good. If you look at the graph on your calculator, you can't see these features, but that's what's going on. To the left of 1/3, you're decreasing, coming down, and you're also concave up. Once you get past 1/3, you're starting to increase, but now you are, and you're still concave up. And then once you get past 2/3, then you are now concave down, and you're still increasing until you get to 1. Once you get past 1, then you start decreasing and you're concave down. In our last example here, we are given the graph of a derivative function f prime of x, and we're being asked to use the graph of f prime to show, shown in the figure, to estimate all values of x at which f has a relative minima, a relative maxima, and inflection points. And we're also being asked to draw a rough sketch of the graph of f with the given derivative. And so what we can do is we can look at our sign charts. Now, our sign charts for our first derivative will be very simple. We're just looking for where is the output negative. The output is negative to the left of 1. Once we get past 1, our output for our first derivative is positive until we get to 3. And then once we get past 3, our output returns to the negative side, right? So over here, all of these outputs are negative. So our critical points are where the first derivative is 0. And so those are at 1 and 3, 1 and 3. And now let's look at the sign chart for the second derivative. And so remember that the second derivative is the derivative of the first derivative, and so the second derivative tells us where our first derivative is increasing or where it is decreasing. Since we know that our first derivative is increasing to the left of 2, all of this is increasing, then we can put 2 on our second derivative, and there we can put a positive value because our our derivative function is increasing. Once we get past 2, my derivative function starts to decrease. So once we get past 2, our second derivative has to be negative. Remember, the first derivative tells me increasing and decreasing, so my graph is decreasing to the left of 1 and then increasing to the right of 1 in between 1 and 3. Once we get to past 3, then we start decreasing. So my second derivative tells me concavity. So to the left of 2, my graph is concave up. To the right of 2, my graph is concave down. So a rough sketch of this original function, right? We don't know what the output is at 1, so we'll just come up here and we'll put a point there. To the left of 1, the graph is coming down and it is concave up. So we can draw something like that. Coming down, concave up. Once we get past 1, the graph starts to go up, but it's still concave up. At 2, we have an inflection point, and then at 2, from 2 to 3, we are still increasing, but now we're concave down. And then once we get past 3, we're decreasing and concave down. And so my graph looks something like that. Okay. So that is it. Oh, I'm sorry. So relative minima, we have a relative minima at x equals -1. We have a relative max at x equals 3, and we have inflection points at x equals 2. There's your homework for this section, section 4.2. Your homework is 1 through 57 odd.